Welcome to this explainer. I'm absolutely thrilled you're here today because we're going to unpack a true marvel of modern engineering. It's something most of us rely on every single day, yet we rarely stop to think about how it actually works. We are diving into the internal combustion engine. But hey, instead of getting bogged down in super dense technical jargon right out of the gate, I want you to think about it using a much more relatable metaphor. Think of it as mechanical breathing. Okay, let's just dive right in. I know, it sounds a little strange to ask how a car breathes, right? But I want you to imagine your car's engine as this powerful, rhythmic set of mechanical lungs. Just like you and I have to inhale oxygen and exhale carbon dioxide to give our bodies energy, your engine has to inhale fresh air and fuel and then exhale burnt exhaust gases to generate the power that literally gets you down the highway. Without this continuous breathing process, well, your car simply wouldn't even start. So, the real key here is understanding exactly how the engine takes those breaths. What we're really talking about is the four-stroke engine. This concept was first demonstrated by Nicholas Otto way back in 1876, which is exactly why you'll sometimes hear it called the Otto cycle. This specific cycle powers pretty much all modern cars and trucks on the road today. And as the name implies, it's called a four-stroke because it requires four separate, distinct movements of a piston: intake, compression, power, and exhaust, to complete one full cycle and turn the engine's crankshaft. Now, before we watch those four strokes in action, let's meet the main cast of characters that make this whole thing happen. What's actually brilliant about this core setup is how simple it is. You've got the cylinder, which is basically just a stationary metal tube that's closed off at one end. Inside that tube is the piston. You can think of the piston as a moving metal plug sliding up and down. And attached to the bottom of that piston is the connecting rod. That empty space between the top of the piston and the top of the cylinder, that's the combustion chamber. That is exactly where the magic happens and where our fuel and air will eventually burn. But you might be wondering, how does a piston moving in a straight up and down line actually make your tires spin round and round? Well, it's a perfect transition from linear to rotational motion. And a great way to picture it is by thinking about riding a bicycle. The bottom of our connecting rod attaches to an offset shaft called the crankshaft. When the expanding gases in the cylinder force that piston down, it pushes the connecting rod, which then forces the crankshaft to turn. It is exactly like your leg pushing down on a bike pedal to turn the sprocket. Your leg just goes up and down, but the wheel goes round and round. So we have our core components and our crankshaft in place. Here is the rhythmic sequence of events. Step 1, intake. Step 2, compression. Step 3, power. And step 4, exhaust. Let's break down each beat of this mechanical heartbeat, starting with step 1, the intake stroke. This is the inhale. The piston starts at the very top and travels downward. As it moves down, it acts exactly like a giant syringe, creating a partial vacuum inside the cylinder. At this exact split second, a little mechanical door called the intake valve opens up. That vacuum forcefully pulls in a fresh charge of air from the outside, mixed with a perfectly metered amount of vaporized gas from your fuel injector. By the time the piston hits the bottom, the cylinder is totally full of this highly combustible air-fuel mixture. And that intake valve snaps shut, sealing it all inside. Next up, the piston reverses direction and heads back upward for stroke number 2, compression. Because all the valves are tightly closed now, that air and fuel mixture literally has nowhere to go. As the piston rises, it violently squeezes this mixture into a tiny little space at the top of the cylinder. And this squeezing process, it is absolutely crucial. Compressing that mixture drastically raises its pressure and temperature. It makes it incredibly volatile and sets the stage for the maximum possible energy release. It is essentially the ultimate setup. Which brings us to the main event, stroke number 3, the power stroke. Just as the piston reaches the absolute top of its compression phase, engineers call this top dead center, a spark plug fires. This tiny little electric spark ignites that highly compressed air-fuel mixture. And it doesn't just casually burn, it rapidly combusts and expands. We're talking explosive force here. These are essentially millions of tiny, highly coordinated explosions that somehow don't blow your car to pieces. That expanding gas violently drives the piston back downward. This right here is the genesis of your mechanical energy. That single downward push is what actually turns the crankshaft and propels you down the road. Finally, we reach the fourth and final step, the exhaust stroke. Our fuel has been burned, the energy has been extracted, and now all that's left is a cylinder full of hot, useless smoke. The engine needs to exhale. So as the piston travels back upward from the bottom of the power stroke, the exhaust valve is forced open. The rising piston acts like a plunger, physically shoving all those exhausted, burnt gases out of the cylinder through the open exhaust port. Once the piston reaches the top again, the exhaust valve closes, the intake valve opens back up, and the entire four-stroke cycle starts completely over. Now, I know I've mentioned these valves a few times, and they really deserve their own spotlight because the valve train is vital. An engine valve works a lot like a tapered metal plug in the bottom of a bathtub. When you pull the plug out of the hole, water drains. When you push it in, water is trapped. An engine valve has a tapered face that perfectly seals against a matching seat in the cylinder head. During the compression and power strokes, these metal-on-metal seals must be absolutely 100% airtight to trap those exploding gases. If they aren't, you lose all your engine's power. But you might be thinking, who tells the valves when to open and close? Allow me to introduce the engine's mechanical brain, the camshaft. It is literally a shaft covered in these egg-shaped bumps called cam lobes. As the camshaft turns, the high, pointed part of that lobe physically pushes down against the valve stem, forcing the valve open against a really stiff spring. And as the lobe rotates away, that spring snaps the valve shut again. This camshaft is mechanically linked directly to the main crankshaft. It typically spins at exactly half the speed of the crankshaft, which ensures those intake and exhaust valves open at the precise milliseconds required for the whole cycle to work. And what's actually really fascinating is that not all valves are created equal. The intake valve is usually noticeably larger in diameter than the exhaust valve. Why? Well, because an engine is essentially a giant air pump. The more air you can draw in, the better the combustion, which equals more power. The exhaust valve, on the other hand, might be smaller, but it is manufactured from a much stronger, incredibly heat-resistant alloy. See, while the intake valve gets cooled off by fresh incoming air, that poor exhaust valve is subjected to a constant barrage of extremely hot burnt gases. We're talking temperatures often exceeding a blistering 700 degrees Celsius. Because these parts operate under such extreme stress and require absolute, perfect precision, things can and do go wrong. If that camshaft timing is even slightly off, or if a valve doesn't seat properly because of some carbon buildup, you are going to notice the symptoms immediately. You might experience a rough idle, engine misfires, or a severe loss of power due to low compression. Or worst case scenario, if your timing belt breaks entirely, the pistons can actually smash right into the valves, bending them and causing catastrophic internal damage. They are small components, but man, they carry a massive responsibility. So, to bring this all back to the core mechanics, let's look at one single, very important number: 2. It takes exactly 2 full revolutions of the crankshaft, that is 720 degrees of rotation, to complete just one single 4-stroke cycle. Remember, each of the 4 strokes, so that's down, up, represents a half turn of the crankshaft. This is a fundamental, unbreakable rule of thermodynamic engineering for the Otto cycle. Now, let's try to put that into perspective with the sheer scale of speed happening under your hood. When you step on the gas and get your engine running at, say, 5,000 RPM, which is revolutions per minute, that means your main crankshaft is rotating a dizzying 83 times every single second. Just try to picture that for a second. A heavy metal shaft spinning 83 full rotations in the time it takes you to, say, 1 Mississippi. It's wild. And hey, if the crankshaft is turning 83 times a second, let's think about the piston. Since there are 2 strokes, one up, one down, for every single rotation of the crank, that means the piston is violently changing direction 166 times per second. It travels from a dead stop at the top, accelerates downward, comes to a dead stop at the bottom, and accelerates back upward, 166 times in a single second. And it is doing all of this while being bombarded by literal fire. Which really brings us to our final thought. The next time you turn your key or press the start button, just take a second to think about the highly choreographed chaos taking place just a few feet in front of you. You have mechanical lungs inhaling and exhaling, camshafts precisely triggering metal valves, and millions of contained explosions happening every single hour. Yet amazingly, this incredibly complex 4-stroke engine operates smoothly, quietly, and reliably for years on end. Given the extreme physics and those dizzying speeds required just to drive to the grocery store, isn't it an absolute miracle that we aren't all mechanics? Thanks so much for joining me on this explainer, and remember to keep questioning how the world around you works.